Hey guys, last time we talked about binomial expansion using Pascal's triangle. Now let's talk about binomial theorem. So binomial theorem is just another way to expand the power of binomials. So if you add a plus b to the nth power, it's another way to expand it. Now in order to understand this, we need to know the formula for combinations. Next week, we're actually going to derive why this formula for combinations works and what exactly combinations are. But for now, I'm going to give you the bare bones of what a combination is. If you have a combination of n objects taken r at a time, it can be either written like this. So it's a combination of n things taken r at a time. Another way to represent this, and this is the way we're going to do it here, is it's kind of like an ordered pair, except it's going to be vertical, where it's n, r, no fraction bar in between. It's just like that. So this is the notation we're going to be using today. This is also acceptable notation. These two mean literally the same exact thing. And the formula for this uses factorials. And we'll discuss why it's this formula next week, but for now, just trust me on this, we'll get there. It is n factorial divided by r factorial over n minus r factorial. And a reminder that factorial just means whatever n is, you multiply all of the integers leading up to that. So if you had 5 factorial, that means 5 times 4 times 3 times 2 times 1. All right? So that's what? 120. All right. So this is combinations. We're just going to be using this notation to help us know that, and you just need to know that's the formula. All right? Now, if we just start messing around with some combinations, let's say we just did the combinations of 3. So if we did 3 things taken 0 at a time, 3 factorial over r factorial, 0 factorial, and then 3 minus 0, which is 3. Fun fact, 0 factorial is equal to 1. We'll talk about why this is next week when we talk about this formula as well. But just trust me, it's 1 for now. We'll go in depth on it at a different time. But that's just 1, so it's 3 factorial over 3 factorial, so that's 1. If we took 3 things 1 at a time, 3 factorial over 1 factorial, 2 factorial, because 3 minus 1 is 2. So it's 3 times 2 times 1 over 1 times 2 times 1. Those divide off, leaving us with 3. 3 factorial over 2 factorial. It's 3 factorial over 2 factorial, 1 factorial. That's literally the same thing because these are multiplication. So it's 3. And then 3, choose 3. 3 things take it 3 at a time. 3 factorial over 3 factorial, 0 factorial. And the same thing as up there. So it's 1. Wait a minute. So it was 1, 3, 3, 1. Hey! That was row 3 of Pascal's triangle. Now, would it blow your mind if we did the combinations for 4 and it came out to be 1, 4, 6, 4, 1, which was row 4? Well, watch this. 4, 0, 4 factorial over 0 factorial, 4 factorial. That's just 1. 4, 1. 4 factorial over 1 factorial, 3 factorial. It's 4 times 3 times 2 times 1 over 1 times 3 times 2 times 1. Those divide off, leaving us 4. 4 things taken 2 at a time. 4 factorial over 2 factorial 2 factorial. 4 times 3 times 2 times 1 over 2 times 1, 2 times 1 times 2 times 1. So those divide off. And then 4 times 3 is 12, divided by 2 is 6. Oh, more than halfway there. 4, 3. 4 factorial over 3 factorial 1 factorial. What? That's the same as that. And 4, 4. 4 factorial over 4 factorial 0 factorial. It's the same as that. 1, 4, 6, 4, 1. That was row 4. So these combinations give us the position in the row in our Pascal's triangle. So these combinations give us those coefficients that we got from Pascal's triangle. So now with this formula, you don't need to do the previous 9 rows in order to get row 10. So the coefficients, well, the terms in Pascal's triangle were the coefficients in our sum. So that's going to help us with our binomial theorem. So our binomial theorem states that if you have a binomial, a plus b to the n, if you were to expand it, it's going to be a bunch of terms added together. Well, last week we talked about a bunch of terms adding together. It was a sum. And an easy way to represent a sum is with sigma notation. So it's with sigma notation. And each term, the coefficient is the power. That was our row. That was our power. And then choose a number. All right. And our number started at 0 and ended at n. That bottom number, the number of things we're choosing, starts at 0, then goes up until we reach n. So it starts at 0, ends at n. And then there's the 2 terms from our binomial. Now when we expanded using Pascal's triangle, the power on a started high and ended low. So it started at n, and every single time we'd subtract an additional value from it. Well, that's what k is progressing as. So it'd be n minus k as your power on a. I'm just going to spread this out a little bit. And then for b, the power started at 0 and increased, so it's k. So this binomial theorem is just another method for expanding a binomial. It's the same as it would be in if you were using Pascal's triangle, except it's more direct. You don't need to use the whole triangle to find out the polynomial, to find out the expansion. This is also helpful if you want to find a specific term in the sum. If you want to find a specific term in the expanded binomial. Let's say we wanted to find the 5th term in 2x minus 3y to the 8th. Well, the 5th term in that, well, the first term is 8, choose 0. So the 5th term would really be 8, choose 4. 2x to the 8 minus 4 times the negative 3y to the 4. And then we can simplify this. That's 8 factorial over 4 factorial, 4 factorial times 8 minus 4 is 4. 2 to the 4th is 16. 16x to the 4th. 3 to the 4th is 81. Y to the 4th. And this is 8 times 7 times 6 times 5 times 4 factorial over 4 times 3 times 2 times 1 times 4 factorial. The 4 factorials divide off. 3 times 2 is 6. The 1 you don't need. 4 goes into 8 twice. So that's 70. So it's 70 times 16 times 81. I don't know that one off the top of my head. 90,720. X to the 4th, y to the 4th. And doing it this way, you didn't need to find out rows 0 through 7 before you got to this term. All right, so that's just binomial theorem. Just another way to use to do binomial expansion. It's more efficient than Pascal's triangle, but it's not as easy to remember as Pascal's triangle. All right, have fun. Bye.